Okay, so thank you for the introduction, and thank you also to the organizers for deciding to put me first so I don't need to sit here nervously all day. I want you to think back to the early days of 2020, maybe to the first time you heard about this new virus spreading from Wuhan, China. Maybe some of your most powerful memories from the time are of empty shelves in the supermarket, or of not being able to go more than 100 meters from your home. For me, one of the most powerful memories of this time is this picture of me wearing all of my personal protective equipment, volunteering at the center that the Weizmann Institute set up to do corona testing. But I also want you to think back to how amazing it was when the first vaccines for COVID-19 came out, allowing us to return to some sense of normalcy in our lives. But do you know how these vaccines work, or what these vaccines actually do? When we're injected with these vaccines, it causes our body to make some kind of bodyguards against the virus. After some time, the bodyguards fall asleep, but that's okay, because when our body is confronted or attacked by the virus, it only needs to wake the bodyguards up, and then the bodyguards are ready to prevent the virus from infecting us. These bodyguards are actually proteins called antibodies. Unfortunately, we don't know how to get our body to make these antibodies or these bodyguards against many diseases, such as many cancers. Therefore, we need to outsource the production of the antibodies. And what I mean by that is we need to make the antibodies outside of our bodies in the lab and give them to our bodies as treatments or as medicines so that the antibodies can fight against these diseases for us. And this strategy of making antibodies outside of the body in the lab and giving them as treatments, we can call antibody treatments. This strategy of antibody treatments is now used to treat a wide range of disorders, ranging from many cancers to neurological diseases to some autoimmune diseases. And by now, more than 130 antibodies have been approved by the Food and Drug Administration for clinical use, which is really a tremendous, tremendous accomplishment. That being said, making good antibodies outside of the body is very difficult. And this is typically a process that's done through time and labor-intensive lab work. And this is a large contributor to the eventual cost of antibody treatments or antibody therapeutics, which can range from tens of thousands to hundreds of thousands of dollars per treatment. And current statistics show that it takes more than 5 years to develop an antibody to the point that it's good enough to be a useful treatment. The reason that it takes so long to develop antibodies into good treatments is that in order for antibodies to be good medicines, they need to really, really excel in a wide range of characteristics. 4 of them stand out as the most important, and I'll go over them quickly here. The first is that our bodies need to recognize the antibody as human, so that our bodies don't mount an immune response against the antibody itself, which could be catastrophic. The second is that the antibody needs to function for a long time at the temperature of our body, at 37 degrees Celsius. And this makes sense because if you imagine that the antibody would fall apart after an hour at 37 degrees Celsius, then we would need to give the antibody as a treatment every hour, which is just not manageable. Third, the antibody needs to bind strongly to its target. And fourth, it needs to not cause any side effects, or not any serious side effects, at least. And making this even more complicated is that antibodies really need to excel in all 4 of these characteristics, as well as others. Being good enough in just 3 out of the 4 characteristics simply does not cut it. To make this even more complicated, there are a huge number of possible antibodies. And this makes sense because our body needs to be able to produce these antibodies to fight against anything that might want to invade it. And it can't know ahead of time what might want to invade it. I'm showing here a cartoon of an antibody. It has a Y shape with 2 arms at the top that each independently binds to their target. But antibodies are not really these cartoons. They're complicated molecules made up of repeating building blocks called amino acids. This is similar to how sentences are made up of repeating building blocks called words. In the case of proteins or antibodies, there are 20 of these building blocks, or 20 of these amino acids. Here, I'm showing a peptide, a small protein made up of 3 amino acids. In this case, arginine, glycine, and aspartic acid. If we look just at the tip of the antibody, just at the part of the antibody responsible for binding to its target, there are about 220 of these building blocks. So that means that there are 20 to the 220 possibilities of different antibodies that we can make. This is really a huge, huge number. And we need to search through all of these possibilities, all of these 20 to the 220 possibilities, in order to find one that's good enough in all of the characteristics that we care about. This combination of having very specific demands that we need the antibody to really be excellent in all of these characteristics and endless possibilities to search through is very challenging. Some of you may be familiar with this from other fields. So it sometimes happens, or it often happens, that we can find antibodies that match most of the characteristics that we need. Let's say that the body recognizes the antibody as human. The antibody functions at 37 degrees Celsius. It doesn't cause side effects, but it just does not bind strongly enough to its target. Now we're at a crossroads. We can either go back to these 20 to the 220 possibilities, go back to searching for a completely new antibody, and hope that we find one this time that's good enough in all of the characteristics that we need. Or we can start from the antibody that we have and try to make changes to the sequence of amino acids of the antibody, to the words that make up the sentence of the antibody, in order to find one that's now good enough in all the characteristics we need. I think we can all agree that this second path seems easier, and so this is what I'll focus the rest of my talk on. But even if we're talking about this second path, about just making changes to an existing antibody, there are still around 10 to the 26 options to scan through. And this is still really a huge amount of possibilities. Currently, scanning through these 10 to the 26 possibilities is done mostly using lab work. But computational methods should be able to more quickly scan through all of these options. And even better, they should be able to predict which among all of these options of different antibodies will be good enough in all the characteristics that we need. Unfortunately, computational methods are simply not cutting it these days. They're not good enough, and they're not making as big of an impact in this space as they should. If we look at what kind of methods people are using these days, the computational methods they use mostly look only at the sequence of the antibodies, or only at the words that make up the sentence of the antibodies. And since we see that this isn't working as well as we should, it seems that something here is missing. And I think that's what's missing from these methods is that they don't take into account that antibodies fold into a very complicated three-dimensional structure. And I think that all of these characteristics that we care about are directly related to the structure that the antibodies fold into. And this is where my research comes in, is in trying to understand how the three-dimensional structure of antibodies relates to all of these characteristics that we care about, and then using this understanding to try to develop methods to better scan through all of these options of different antibodies that we have and predict which ones will be excellent in all of these characteristics. But in order to do this, we need to translate this very complicated structure that antibodies fold into something that's manageable for a computer to sort through. And so in order to do that, we take this three-dimensional structure of antibodies and represent it by the locations in three-dimensional space of all the atoms that comprise the antibody. Once we have this, we can use equations from chemistry and physics to derive a score for this antibody. And using this score, we can then scan through all these different possibilities and predict which ones will have beneficial changes. So far, we've used this strategy to develop computational methods to optimize the humanness and stability of antibodies. And we recently published this method, and we even developed it into a web server that academics across the world are currently using to produce better antibodies. In addition, we're working on developing methods to make antibodies bind more strongly to their targets. And so far, this has been really good and it's been really successful. But if I had to summarize my PhD so far, I would say it's been kind of like this. People come to me with problematic antibodies that are maybe okay, but they're simply not good enough. And I do some magic on the computer and I return to them antibodies that are really, really great. But this has been kind of like being a car mechanic, where people come to me with broken cars and I need to return them a nicely working car. Now, I'm trying to flip this model on its head. I'm trying to take everything that we've learned about antibody humanness, stability, and avoiding side effects, and use it to design a huge garage of perfectly shiny cars, of antibodies that are really excellent in all of these three characteristics. Now, people need to just come to us with their target, with the thing that they want the antibody to bind to, and search through our perfectly designed garage of shiny antibodies, of perfect antibodies, to find the one that binds to their target. We hope that this approach will really cut down on this 5 years needed to develop antibodies into good medicines, getting better antibody treatments into the hands of patients faster. Thank you for listening, and I'm happy to answer any questions.